Just wanted to give you a brief rundown of how you can do lab number 4, ADD converters with serial port output and plotting. Without the audio shield, we can do this in simulation. What I've got here is a potentiometer, also known as a pot. You can see the potentiometer off to the right here. It's a basic component with a wiper, and what it does is it takes this tap analog input 0 from the center, and it uses its little wiper as a voltage divider to go between ground and 5 volts. As it does that on a 10-bit input, you get 2 to the 10 or 1024 different possible inputs to the ADD converter, which you can convert into a integer that ranges from 0 to 123. What we do here is we let's take a look at the code. We use a serial output, and we're able to I'll just comment some stuff out here. We're able to input from the analog to digital converter input 0 using analog read. So if you look at it, it says A0, so that's what analog read of 0 does. That gives me a value, right, which is going to range from 0 to 1023. And I'm going to divide that by 100, and so that will be equal to a value that ranges from 0 to 10.23. So that's the range. Then we go in over here and we say let's multiply it by 0.01. Right? So if we look at it that way, V times 0.01 is going to now be equal to a range that goes from 0 to I'll say 0.1023, or maybe we should say 0.1023 so we don't confuse it too much. So in other words, we can go to a tenth as an increment, a tenth of a radian, right, as the increment. And let's see now. 1/10 of a radian, I don't know what that is in degrees. I think you have to multiply by 180 divided by pi or something like this. So what is that, 18 degrees or something? I forget how to do that. Radians to degrees is, yeah, you multiply by 180 divided by pi. So the pi part goes out, and then you have 180 times 0.1, so that gives you like 18 degrees. That's a tenth of a radian. And so that'll be used as the increment for theta at maximum. And minimum will be a 0 value. In other words, you won't be incrementing theta at all. And theta will keep going until it gets to 2 times whatever this number is. Let's call it pi. As a matter of fact, it makes more sense to actually use the term pi. And then, if you like, you can define pi, perhaps something like this. Pi, as it's uppercase, equals, what is pi equal? 3.1419265358962643383273, something like this. And so, and you need a semicolon. So now we've got pi in there, 2 times pi. In fact, we could even call this, since we're doing the computation all the time, let's call it pi 2, just so that we don't have to do the computation of multiplying by 2. So pi 2. There, saves us a little multiply. Then we take the sign, and probably want to throw in a delay in here if you're going to do this with real hardware. delay of 50 milliseconds. If you're not going to use real hardware, it kind of doesn't matter. And if you're going to use the serial plotter, you got to close it if you want to open up the serial monitor. So let's take a look and see what happens here. So we'll get the serial monitor open, and I think there should be a plotter in there. Oh yes, there's the plotter. You can open both in the simulator, but you can only open one of them in the real hardware because that causes what you call a serial port contention issue. So let's start the simulation. It seems to be working. Let's stop the simulation and move the hardware over. The hardware, it's in the way. I wonder if you can just take the whole thing and wish you could take the whole thing and just shove it over. Oh, you can. Okay, let's do that. Stop it. There. Gotta hit escape to stop that. So now let's start the simulation. Open up the code. And, oh, this is still moving. It won't stop moving. This is fun. All right, we're going to get this pot and we're going to move it over. I think I'll just shove it over here so it's not in the way of the code, even though that looks ugly. And then we'll go over in here and we'll start the simulation. We'll open up the code. We'll run the pot down to 0, and we can see it's changing values. All right. Now what we're going to do is we're going to open up our little there comes the sine wave. And if you reduce the increment, you should change the... What you want to do with this? This is going too slow. Let's stop the simulation, and for the sake of simulation, get rid of this delay. There you go. Now let's run it again. We're starting to see a sine wave here. Let's increase the frequency a little bit. And that looks like it's got a slightly shorter wavelength, which is just what I wanted. And now what we're going to do is we're going to stop the simulation, and we're going to square off the sine wave. We're going to say if d is less than 0, d equals -1, otherwise d equals +1, and now we can see, aha, that looks an awful lot like a square wave. So we've squared off the sine wave. Now we're going to reduce d, and that lengthens the duration of the square wave. Let's see if that works. And sure enough, we can see the square wave is changing in frequency. And that's it. So basically, for this lab, you would use both the sine wave and the square wave and show the two different kinds of code that you've got. And that basically is the lab. Gives you a little output, shows you how to do some input. You can do some plotting. And it was supposed to be a very short, very easy lab. But interestingly enough, some people got really stuck with this one. So I was kind of glad we didn't ask too much of you during the lab session. And that's what we've got. So hope you like my little demo. Talk to you later. Bye.